All right, this is a solution to the AP Physics 1981 problem, electromagnetism. It's number one. You're asked to find a couple things here. Well, first of all, here's the setup. You've got a conducting shell, conducting sphere. It has radius A. There's an outside concentric shell, also conducting. It has an inner radius of B, outer radius of C. And you're asked to first find the electric field in between the space from A out to B. Then you're supposed to find the capacitance of this configuration. And then I drew this here. Then part C, you're going to find the capacitance of a new situation. And the new situation is that the capacitor has been filled with some oil, dielectric oil, and it has a coefficient of 4. And so we'll talk about how that changes things. Also, just a little reminder, the sphere has a charge of Q. You're going to ground the outside and then remove that grounding wire. The reason they do that, they tell you they want you to know that the outer shell has an electrical potential of 0. So the first part, finding the electric field between A to B, that's using Gauss's law. And that's something that we've done many times. Just as we look at this, we note that the electric field is parallel to dA, so we can get rid of the dot product and write it that way. And the electric field is going to be constant at any given R. We then add up all of the little dAs, and that's basically the area of our Gaussian surface, 4 pi r squared. And we have a statement for what the electric field is. First part shouldn't be too difficult. We've got the electric field as a function of R. The second part, we're supposed to find the capacitance of this particular geometry. Again, reminder, the inner sphere has a charge of Q. And then we, by definition, called the outer shell an electric potential of 0. So, your go-to question anytime you're asked something about a capacitor is, how does a capacitor function? And we know that that's the ratio of Q over the electrical potential difference. And yeah, just a little reminder here, we always have this habit of writing V. We mean this. And this is actually going to cause us some problems when we start dealing with that negative sign. I notice that sometimes as I go through this, because I take shortcuts, that confuses some students when we start dealing with that negative sign. So here's what we've got. So we're going to start with this, and this is not how you traditionally see this. I think most times we will go and we'll write something like this. And okay, that's all well and good if everybody knows exactly what we mean by this, but the problem is when you're first learning this, you don't know exactly what all this means. So it's not trivial. So what I'm going to do is I'm going to go ahead, rather than just put that down and trust that, oh, okay, everybody knows that that's electrical potential difference. I'm going to write out in its full glory here. And I'm going to note a few things. First of all, that E is parallel to R, so we can drop the dot product. This right here, okay, that's about the simplest integral you can do, but I'm going to write it out this way. I'm going to tell you that this is our final electrical potential, this is our initial electrical potential, and that's going to correspond to the, when R is at some initial position, that's the potential at that position, and then we're going to look at the final electrical potential at some other position, R. So when we work through this, okay, we've already evaluated this. This right here is fairly simple. These are all constants. We have dr over r squared, and that ends up being negative 1 over r. These two negatives cancel out. Evaluate this, and so far so good. That seems pretty straightforward. The reason I did this, though, is a lot of times, and I think that I try to avoid this, but I think that I'll fall into it too. I'll get lazy and sloppy and start skipping steps. This right here, this is your final position. It corresponds to what is the electrical potential at that final position, and then likewise for where we are initially. You can start here and move out to here. If you do that, if you start here at A, at the surface of our conducting sphere, and you move out towards our shell, because you've been told that the inner sphere has a positive charge, you know that the electrical potential should decrease the further away you get. And that doesn't matter. You can go from here, here, or from here, here. If you're heading in this direction, the electrical potential is going to decrease. There is a drop in the electrical potential difference from here to here. If you go from here to here, the electrical potential difference is going to increase. But if we describe the electrical potential right here at B as being 0, it is grounded. That means that's how we indicate electrical potential of being 0. You should get the same value for the electrical potential right here at A on the surface of our sphere. So let's take a look at that. And I'll go back and forth with our little diagram there. So if we let the outer shell have an electrical potential equal to 0, and you want the electrical potential difference moving from A to B. In other words, we're going to go from here out to the shell. You must realize that the electrical potential will decrease. So let's start plugging in some values here. This is our final electrical potential. This is our final position. So this is what we're doing here. Reminder, since the electrical potential at B is equal to 0, so this is equal to 0, we can simplify things. We end up with a statement like this. Here's where things, it's a little subtle, but you've got to notice this. B is bigger than A. B is further out. A is smaller. And so this is going to be negative. What we end up with is showing that the electrical potential at A is going to be positive. It has to be at a higher potential. Okay, that's all fine. We went from A out to B. What if we went from B into A? So a little reminder here. This is our statement about how we identify the electrical potential difference in terms of where we are. In this case, we're going to go from B to A, so that's from the outer shell inwards. Your electrical potential is going to increase. So you're going to have a positive change in the electrical potential difference. This is going to describe our situation. But, reminder, the electrical potential at B is defined as 0. So, hey, we end up with the exact same thing. This shows that BA is at a higher potential. It's the same thing that we got when we went in the other direction. So hopefully that takes care of some of the confusion around that negative sign. And just real quick, the other part of this problem, where you're supposed to find the capacitance of the new situation here. Well, when we fill the capacitor with oil, and you're told that the dielectric constant is 4, you are really making 2 new capacitors. You've got 2 capacitors that are in parallel. And because of the fact that they're in parallel, all we have to do is find the capacitance of the top half and the capacitance of the bottom half here and add those together. So since we've cut our original capacitor in half, we can say that the capacitance of the top half is 1/2. The capacitance of the bottom half is also 1/2, but we have to modify it by that dielectric constant, then add these 2 together, and you end up with 5/2. 5 has the original capacitance, or 2.5 our original capacitance.